Hi, welcome to our talk on Newtonian gravitation. What are we learning? We're going to learn about the fundamental forces and how to calculate the force of gravity between two masses. First, let's look at the known fundamental forces of nature. These basic forces are what we call forces at a distance. They do not require contact. The first of our fundamental forces is called the electromagnetic force. This is the force that involves electric and magnetic fields. Electric charges can be positive or negative. Negative charges come from electrons that we'll find orbiting the nucleus. Positive charges come from protons that we find in the nucleus of the atom with the neutrally charged neutrons. Like charges repel and opposite charges attract. Now we say that forces at a distance do not require contact, but even contact forces such as friction, tension, the normal force, etc., things that we've looked at before, they actually come from the electromagnetic force at the atomic scale. So if you look at the atoms, let's say holding of an object in your hand, it involves the outer electrons of the atoms of your hand being repulsed by the outer electrons of the object. So to summarize, the electromagnetic force is a force between charged particles that may be in motion. And most forces that we see are from the electromagnetic force. So where does magnetism come into this? We call it the electromagnetic force. So where is the magnetism? Now, if we have an electric charge moving, it creates a magnetic field around it. So if we have a current carrying wire and electric charges are moving, the blue lines represent the magnetic field formed by those moving charges. Again, more on this later. We'll get way into this. One more thing about the electromagnetic force that we'll see later. When a negative electron interacts with a positive proton, the electromagnetic force adds energy to the electron, producing a photon. Don't worry about this now. We'll get into this a lot more later. Another of the known fundamental forces is a much stronger force than the electromagnetic force that happens in the nucleus of atoms. It's called the strong nuclear force. The strong nuclear force overpowers the repulsion between protons, and it is about 2 orders or 10 to the 2 times stronger, that's 100 times stronger than the electromagnetic force. It's the glue that holds the nucleus of an atom together. The strong nuclear force is negligible for distances more than about 10 to the negative 14 meters. One more thing about this. The energy released when we break these bonds is released as gamma ray photons and neutrinos when this bond is broken. We'll be looking into nuclear reactions in more detail later. I just wanted you to get an introduction to these different types of forces. Now, there's another of the fundamental forces that takes place in the nucleus of the atom, but it's weaker than the strong nuclear force. And what do we call it? We call it the weak nuclear force. It is a very short-range nuclear force, and it has to do with the radioactive decay of protons to neutrinos. When a proton is turned into a neutron, it releases a positron and a neutrino. Again, way more about this later. I'm just giving you an introduction here. This is also negligible except for really, really tiny distances, about 10 to the negative 17 meters. Finally, we get to gravity. Gravity is an attractive force between two masses. It is the weakest of the fundamental forces. Now, if two particles with masses m1 and m2 are separated by a distance r, a gravitational force F acts along a line joining them, with a magnitude given by this equation here, where g is a constant of proportionality, and it's called the constant of universal gravitation. And notice it's a big G. Now, the gravitational force is always positive, but notice it's small. No matter what we multiply all of this by, we're going to multiply it by something times 10 to the negative 11. So that's going to make it really small. We need one of these masses to be very, very large before we can really measure it. This force is an example of an inverse square law, in that it varies as 1 over the square of the distance between the particles. Now, from Newton's third law, we know that the force exerted by M1 on M2, designated F12, is equal in magnitude but opposite in direction to the force F21 exerted by M2 on M1, this forming an action-reaction pair. Another important fact is that the gravitational force exerted by a uniform sphere on a particle outside that sphere is the same as the force exerted as if the entire mass of that sphere were concentrated at its center. Let's try solving a problem using our new equation. Let's say we have two masses, M1, another one, M2, and let's say M1 is 2 kilograms, and M2 is, let's say, 4 kilograms. Let's put them a distance of 1 meter apart. What's the force of gravity between these two masses? This will be F2 on 1, F1 on 2. Here's our equation. Our equation is solved for what we want to know. Now let's just plug and chug. Now you may be wondering how we got newtons out of all of these different units here. So to do a unit analysis on this, we're just going to take just the units and go through the equation with them. Meter squared cancels out. That gives us meters, 1 meter there. We have a kilogram here. I'll take care of 1 kilogram. Let's rewrite this now. This is a Newton. All right, let's summarize what we've learned so far. First, there are 4 fundamental forces of nature that we know of right now. The strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Now, gravity is an inverse square law. It is described by this equation here. It is the force of gravity between two masses, represented by these vectors. We take g, the gravitational constant, which is this number here. We multiply it by the mass of one object times the mass of the other object, and divide it by the square of the distance between them. All right, thanks for listening, and complete your Cornell notes, rewind, and review as necessary.